keep going on about our lecture last week. So I try to cover some important concepts about the neural network so that when you train your own networks, you can also know the theoretical ideas about why those neural networks work. Alright, so let's recall our lecture last week. So we have the linear classifier already, and we also know how to create a loss function to help us to improve the classification accuracy. And we also know how to use regularization terms to get a balance point between data loss and the parameters. And we also learn some stochastic gradient descent methods to optimize the parameters of our model. Okay, now there's a problem. The linear classifiers are not the most powerful tool for image classification. There are some examples, and this is one of them. Say, if we have two classes, and the green circles belong to one class, and the blue circles belong to another class, although there are only two dimensions. Okay, so for this case, how do you create a linear classifier to class the two classes? No matter, okay, how you, okay, let me try. Draw a line, okay, like this is a linear classifier, but it doesn't work very well. Okay. Or you can try other linear classifier. Here or here. Okay. You cannot classify the two classes very well because of their distribution. Okay. So how to do it? One way is to transform those features. Okay, here we can transform the Cartesian coordinate into polar coordinate system. So this x, y, usually we say is a Cartesian coordinate, and the two axes are orthogonal. And we use the equation. So this is the radius from the origin point, and this is the angle. So if we use the feature transform function to create a new coordinates like this, then those green dots will be somewhere here because they are very close to the origin point in its original Cartesian coordinate system. And those blue dots will be somewhere far from the original point, so their radius are slightly larger. Okay, here we can find a linear classifier. It's just a hyperplane to separate the two classes. Okay, so this is something why neural network will work, and I will you will see some examples in the following slides. Okay, so let's go back. What will be the useful feature to describe an image? Say color, right? Because for different objects or different kinds of images, usually they have their own colors. So remember last week we see the hug feature. It is a histogram of gradient. It can describe a shape, okay? But it cannot describe a color. So there's another kind of feature, use color. So this is a color histogram. For this frog and its background, because the frog is green and the background is also green. So in the histogram of color, there will be many green pixels, and the beam of the green spectrum will be very high. Okay, so we can describe images using some feature like this. We usually call them low-level visual features because they are very basic. They can see this. If we use color histogram, can you know the shape of the image? No, you cannot. You can only know the distribution of color. And if we use hug feature, then we roughly can know the shape, but we cannot know its texture or its color, or even there are some patterns on the image. Okay, so before neural networks, there are many researchers, they try to combine those low-level visual features to create an effective descriptor just feature to describe an image, and then try to use some machine learning algorithms like SVM to do the image classification task. So there was a very famous feature called bag of word. Okay. Here, what you see is bag of visual word, and the idea bag of word is developed from text retrieval. It means if you have a lot of documents, and because you know a document consists of many paragraphs, and many paragraphs consist of many texts. So it means, how do I know two documents are similar? One intuitive way is just to compare their words. If they share many repeated words, the two documents may be very similar. So the idea was borrowed by the computer vision community. They created a bag of visual words. What is visual word? So it means, given an image like this car, so it crops a lot of patches from the car, like this one. Okay, and this is the image of a frog. So it crops a lot of patches from the frog. So you can collect a lot of patches and create some codebook. Codebook means some patches, they occur very often. The frequency of those patches are very popular among the bag. Okay, so once you have a new test image and you would like to know which the class the new test image belongs to, okay, you don't need to compare image by image. You just need to compare the image with those existing bags and find the most similar one. This is, for example, if I have a codebook like this, and given a test image, I can use those codebook to encode the image. So like this one, see the bars. Some of them are high and some of them are low. It means I count the number, how similar given a patch, and I can find how many patches in the test image. Okay, so this is a way to create a feature. I use the bag of patches to describe a test image. So see, you can have color histogram as one feature, and histogram of gradient as another feature, and the bag of words as the third feature. So it means you have three vectors. Okay? You can combine the three vectors, become your image feature. So you can see here 1, 2, 3, and I combine all of them. Okay. So let me talk about something before neural network. So this is the winner of, okay, so this is the ImageNet challenge. ImageNet, the dataset was combined, released in 2008. So it is the fourth year. Every year, they hold a challenge. They invited all researchers in the world to compete with each other whose algorithm was the best one to achieve the best accuracy for image classification. And AlexNet, okay, the first famous neural network method to solve the problem, was published in 2012. So this is the winner of the challenge before AlexNet. So let's take a look at how they did. Okay, first, they check the shift feature. So shift feature is scale invariant feature transform. So shift feature is very useful for image matching. It means given an image and you want to find a similar image in a data set, then many people will use shift feature. And also here is color. So they extract the feature and use principal component analysis to reduce the dimensions. Because still remember, there is a term for curse of dimension. If your feature dimension is very high, it is very difficult to deal with those features. So so let me show you a figure about the principal component analysis. Okay, so you can find the sections of principal component analysis in our textbook and our reference book. Okay, so it is a useful tool or useful concept. The idea is you have a bunch of data, say several millions, okay, and the dimension of those data are maybe very high. Okay, you say 100 dimension or 200 dimension, but you are wondering whether you can find another representation for those data. Maybe like this. Okay, maybe those data, their distribution follows some property. You can find a most significant direction to describe them. For example, for this bunch of data, okay, see, they are mostly on this direction. Okay, and then if we use this direction to represent those data, yeah, we approximately almost know how they distribute, and then we are going to find other directions to describe the bunch of data. So our principal component analysis, it aims to present the same data with limited loss. Okay, but if you want to, you can reconstruct them approximately accurate. So let's go back here again. Here, TCA is used to reduce the loss data, and then it uses feature vector to. Let me see here. Given an ImageNet image, so let's take how large is an ImageNet image? So there are maybe 1 million images in the data set, and the average image size is around 470 by 390. Okay, so it's not a very small image. And from just one single image, we can extract a lot of local or low-level computer vision features from. So from an image, it can extract 10,000 patches from the image. For a patch, it can calculate a feature. So see, the size of the low-level features is very large. Okay, so it not only needs to reduce the dimension of each feature, it also needs another presentation to describe the bunch of low-level visual features. Okay, so it uses feature vector here. Okay, So what is feature vector? It means, see here, there are some parameters. First is the number of Gaussian models. So let's take a look at what is mixture of Gaussian model. It means you know Gaussian distribution, right? Okay. So if your data distribution is not just one Gaussian distribution, it is a mix of several Gaussian distributions. So like this one. Then you see the blue curve. It is a Gaussian distribution. And the green curve is the second Gaussian distribution. And the blue curve is the third Gaussian distribution. So if you have a bunch of data and its distribution is like this, of course, you cannot just use a single Gaussian model to model the distribution. So the mix of Gaussian models just means you find some Gaussian distribution as a mix of that, so that they fit your data very well. So there are some parameters. First is how many of Gaussian distribution you need to use, and what are their coefficients or their weights. Of course, they will not only just one by one. Okay, some distribution will be more significant and some will be less significant. Okay. So this is the second reference book we mentioned in very early of this semester. Okay, and you never see it before, but now okay, this is when we discuss about something model fitting, this reference book will be very useful because the book focuses on models and its distributions. So if you are interested, you can take a look here. Okay, so let's get back. So the winner used 1024 Gaussian distributions to model the just one image. Okay, and since the dimension of one feature is 64 already, so you can see the dimension of the feature extracted by just one image is around 525K. So it is very, very long feature vector. And use SVM with the statistical gradient descent to learn a classifier. Or I should say, learn many classifiers because ImageNet has more than some different settings. One is 100 classes, 1,000 classes, and 10,000 classes. Okay, so in 2011, I think the 1,000 classes are available. So they need to train one VSO SVM for 1,000 classes. So they train a lot of classes. Okay, then when a test image is given, they try the 1,000 SVMs and see which get the highest score, and it assigns the classes to the image. Okay. All right. So that's the performance. Okay. What to say? Here, this is a paper of the winner. See, the method was published in 2011. Okay, but I cannot find the performance of this method. After reading the paper, I find another table. Okay, so this is another large dataset called TELTEC 2056. So in the year of 2011, there are several image classification datasets. One is ImageNet, and another is TELTEC 256. So let's take a look of the properties of the two datasets. So see how the image size is slightly smaller in the caretaker 255 datasets, and the total number of images are also smaller than the ImageNet. And okay, the number of classes is also small because the dataset was published in 2007. So you see, ImageNet in 2011, they continually compile many images into their dataset. So it keep going larger and larger. But the caretaker 2006, it might be the state-of-the-art image classification dataset in 2007, but 4 years later, it was exceeded by other datasets. But we can still see, okay, some interesting numbers here. So the SF shift plus local color statistic is the method described on this slide. And there are some existing methods. You can see they were published in 2007 to 2012. Okay, and you can see compare with their performance the feature vector and using shift and color features achieve the best performance. Okay. So let me mention somewhere why feature vectors works well. Okay, one reason is feature vector can create some non-linear feature transform. It is the same as neural networks. Okay. So both of them share the same property, but it was not explained explicitly in our textbook. But there is an interesting paper. Let me just show you. Okay. The paper discusses the property. Okay. So first of all, this paper was published in CPR 2016. Okay, so in 2016, there are many discussions about neural networks already, and this paper proposed an interesting feature. It calls layer-wise relevance propagation. So the feature can be used for what? It can be used to tell us, okay, if we use feature vector, so what is the attention of the feature? Okay, so this case, so you can see this is a rider riding on a bike, right? So if they train a linear SVM classifier to class bike and set the image into it, then what the SVM will pay attention to. So from the heat map, you can see the SVM classifier they see some features of a bike, like this one, where the wheel and the bar of the bike. Okay, if they use the same image, but use the support vector machine, the classifier, of person, then what will the classifier see? It will see, the red region means it pays attention to. It see her hip, his head, her head, her hand, and her torso. Okay. So again, for this image, if it use the classifier of a cat, then what does it see? It see the region, the cat, okay? And it use the person's classifier. What does it see? It see her head, shoulder, and elbow. Okay. So this paper tells us, okay, the feature vector and the neural network, they see different features. So for this image, if they want to classify a sheep, then the feature vector see the texture. You see, there are a lot of wooden of the sheep, but the neural network see what? See the shape of the sheep. Okay, so for the two images, you can see the same property. Okay, so let's go back to our slide. Okay. So what I want to share with you is feature vector and linear neural networks. They work because they have some nonlinear properties. Okay, so so this is the winner of 2011 for image classifier, and this is the winner. Is AlexNet of the same dataset just 1 year later. So they used two different approaches. One is they create some handmade low-level vision features and use machine learning algorithms to train classifier. And then another is just use neural networks. The neural networks include two parts. The first part is it extracts the feature by its own self, and it learn the important parameters in terms of classifiers. So it combines the two steps into single one structure. Okay. And this one, the B, is the winner of 2011. It creates the feature shift and color, right? And use the feature vector is also included in this part, and they use supported vector machine to learn the parameters for classifiers. Okay, so I hope you can see the big picture. It means now we are going to cover this part. How do we use neural networks to extract feature and tune the parameters at the same time? Okay, so let's discuss about the definition of neural networks. So suppose we have just like the CFA10, we have many images, and for those images we can assume it is a very, very long vector. So I just use the dimension of D to describe an input image. Okay? What we want is we are going to create a function f, so that given an image, or just so it's a very long vector, then there will be several numbers. So the numbers is what? Imagine when you use linear classifier, it is the score, right? The score generated from it, and we convert those scores to loss functions. So that's what we did before, is just use a linear classifier. It means our parameters W are just multiplied by the input vector and plus a bias vector. So if our input vector is the dimension of D, then here our weight is dimension D times C. C means the number of classes. Okay. Now, okay, if we use a ReLU function, it means the max of 0 and the weight. Okay, then we create a two-layer neural network. It's very simple, just two layers. Okay. And if we repeat it again, it means, so for this part, it is, you can think it is feature. Okay. For some cases, the feature values are 0. And for some other cases, the feature values are just like the linear case 1. And the outer layer, you can just imagine. It is a linear classifier. See, do you see the same format? They are the same. For a linear classifier, you have the feature and times a weight matrix plus a bias vector. So see, this is a weight matrix and this is the bias vector. So for the two-layer neural networks, the inner section region, you can see it's just we just try to create some features. Okay. The format of the feature is very similar to a linear classifier, okay. But the only difference is the max function here. Okay. And if we repeat again, so this will become a 3-layer neural network. Okay. If we draw a figure, it will like this. So this is the first layer. Given for the CFAR10 dataset as example, the resolution is 32 by 32, and there are 3 channels RGB. Therefore, the pixels, or should say, the number of value for image, it is 32 times 32 times 3. So the total number is 3072. Okay, so this is input image. Okay, and the first weight matrix W1. Okay, we times our input image plus bias vector B. Okay, so we can generate this part. And if we use the max function in additionally, then this will generate a hidden layer. Okay. So here we can control how many number of the hidden layer we want. Say if we create a matrix, the input is 3077, and the hidden layer is 100. It means the edge here is 100. Okay, so we create some values. I should say 100 values here. And we use the 100 values to repeat the equation again. Say C, for the CFAR10 dataset, there are only 10 classes. So the C here is 10. So D is 3072, H is 100, and C is 10. Then we can generate a 2-layer neural network with output is a 10 by 1 vector. So here, okay. Since there are 3072 elements on the input layer, okay, so the value of the element of an the one value in the hidden layer, it is calculated from all of the 3032 values from the input layer. Do you agree with it? Let's see again. Okay. Here, we use all of the 3072 elements from the input image. This is the X. And we times the matrix W1 here and plus B and use the matrix max function here to create 100 elements in the hidden layer. So for every element in the hidden layer, how is it come from? It comes from all of the 3032 values here. So do you agree with? So for every element, we will, all of the elements in the input layer will be used to generate an element in the hidden layer. Okay, so for this structure, it has a special name. It means multi-level perception. So you may wonder, why is it called multi-level perception? How does the name come from? Okay, so we have to go slightly back to the history. So in the beginning, there are two terms. One is single layer perception. So the structure is like this. You have several input value, and with a weight, and sum them up plus a bias value. So all of them here are values, single value, and you generate an output value. So what is this? It is a simplified case from the multi-layer perception. So do you got it? If I remove all this part, just forget them. Okay, and just take a look of this element and this output element. So it is the single layer perception case. Got it? Okay. So here, the multi-layer perception is just an extension from the single layer perception. Okay. So, and let's go back again. In this case, we use all the input element to calculate, to compute an output element in the next layer. So you will see it is named multi-layer perception, and it has another name. It's for the fully connected layer. So okay, now we have a two-layer neural network, and before the two-layer neural network, we use linear score function for classification. Okay, and let's take a look. So if we use the linear score function, what will be the direction or for those classified? It looks like this. So you have 10 classes, and the average of those images belonging to the 10 classes will like this one. So this is why the host cases, you can see, is almost the overlapping of two host images. One is facing left, and another is facing right. Okay. Now let's look. So suppose you train the two-layer neural network using the CFAR10 dataset. Okay. Since you can do it right now, because you know how to create a loss function, you know how to use gradient descent to slightly reduce the loss function. So if you train the two-layer neural networks, what will you get? Okay. It means from at this hidden layer, you will generate some patterns like this one. It means just proper. So there are 100 elements here in the second layer, right? For each element, you can see what are the input images will create a very high value in the second layer. And from those trained templates, what can we see? Okay, so this is a template, and this is another. So from the two templates, do you see? It looks very like a horse facing right, and this is another horse facing left. So, okay. So what does it mean? It means you have a data, and you have the method to gradually train something meaningful. And okay, the intuitive meaningful is okay. the neural network will try to extract the most influential structures from your training data. But however, I should say, for some other templates, it's sometimes we really don't know what they mean. Okay, now if we concatenate, I repeat the layers one by one, we can create a very, very low depth neural network. So that is why it's called deep learning. Okay. However, let's see. If we don't have the max function here, it is a nonlinear function. Okay. Why? Because if we draw the max function here, it looks like this one. For values less than 0, the result will be 0. For values greater than 0, it will keep the same. It doesn't change. And we call the function, the nonlinear function, activation function here. There are several different activation functions. And imagine if we don't have the nonlinear function, then what will our two-layer neural network become? So this example, let's take the max function off. Then it will become W2 times W1 times X plus B1 plus B2. And let's expand it. It will become W1 times W2 times X plus W2 times B1 plus B2. So see, this is still a linear function. So without the nonlinear function, if we just concatenate all of these linear functions, we will still get a linear function. Oh. So let's show you some popular activation function. So you see ReLU, okay, this is one. And then there are sigmoid, tangent edge, and leaky ReLU, and soft plus, and ELU. So you can see they are somehow similar in terms of what? In terms for values less than 0, it will assign a 0 or a value very close to 0. It just means suppress the value here. For value greater than 0, it either keeps it the same, okay, or make it slightly larger, even the value will converge somewhere. Okay. So the nonlinear feature, it will be used to do something like the feature transform, and I will show it later. So if you want to just create a neural network, it's not difficult. Okay, so there is an example. This is the Python demo code. Okay, they're given some numbers, how many dimensions, and what is for input, and what is dimension for your output. Okay, you can just create 2 layers. So it is the X and Y for your hidden variable. And you create 2 weight matrix. And say you want the gradient descent stop in its 10,000 steps. Then, okay, you set here. This is the okay. Let's see. Okay. So remember, this is our what's that? LDAR boosting factor. All right. Okay. Let's take a break. you want to create a neural network, it's not very difficult. So this is an example. So this is the initialization part. And last, you can see this is the last term. So, and this is the sigmoid term. Remember the sigmoid function? Okay. And then you can compute the gradient and use the statistical gradient descent to update your matrix, weight parameter matrix W1 and W2 here. Okay. So this is just a neural network. It is not a convolutional neural network because we still didn't use any convolutional operator here. And okay. So Justin Johnson here mentions some relationship between biological neural net and the computer neural network. And this is the figure for the biological neural network. There are some input for a neuron, and once they receive those signals, okay, there is a cell. It will do something very similar to the activation function. It will suppress certain signals and relay the signals to other neurons later. Okay. But however, our ReLU or other activation functions are very simple mathematical equations. In a biological neural network, it is very complex. Okay, it may not be just a increasing function. So, what I want to say is, our artificial neural network is an imitation to the real physical biological neural networks. And the biological neural network can be very, very complex. It's not just like our structure is layer by layer. Okay? So some researchers, they also want to do, can they create neural networks as complex as the biological neurons? Yes, and some of them really did it. So there is a paper published in 4 years ago. Okay, they tried to develop the complex structure for neurons, not our convolutional neurons layer by layer. Okay, all right. So let's talk about something important. Is why nonlinearity works for image classification. Okay, remember the example of feature transform, like this one. We transform the feature. So for here, what's the feature? It is the coordinates on the Cartesian system. And we transform them to the polar coordinate system. So for every point here, we got a new coordinate here. Okay. Something similar in the neural network space. Okay, this means, say if we have a linear classifier, okay, and suppose we have two classes. So we have two linear classifiers, as shown as the two hyperplanes, the red one and the green one. Okay, so the two hyperplanes separate the Cartesian coordinates into 4 regions, A, B, C, D. Right? Okay. If we use just feature transform, then we can create a new coordinate like this one. A means for positive H1 and positive H2, and D is positive H1 and negative H2, etc. Okay, so suppose we have many instances need to classify, and we use feature transform. This means that we create a matrix to convert those coordinates from x1, x2 to h1, h2. Okay, and suppose this is their distribution. Okay, if we have a nonlinear function, say ReLU here, then let's see what will happen. Okay, so for the region A, if its new coordinates values are both positive, then it will keep the same, nothing change. But for region B, if it's so let's see what happens for region B. So let's see for any point in region B, what will be its H1 value? Its H1 value will be positive, right? And this H2 value will be negative. So how to see? So since this is the new coordinates, okay, and for this point here, so its H1 value is this one, so it is negative, and this H2 value is what? Is positive here. Say, okay, suppose I have a point here, and its coordinate is what? Say negative 2, suppose this, and positive 2.5. Okay, so its H1, it means the value is negative, and its H2 coordinate value is positive, right? Okay, but since we have maxed the nonlinear function here, then with the nonlinear function, what will happen? It means all values less than 0 will become 0. Okay, so it means what? It means all of the points here, it will be moved to here. Okay? Again, so for the region D, all of the values here will be moved to here on the axis. Okay? So for region C, all of the points here will be moved to the original, because either H1 axis or H2 axis, their values are less than 0. So all of them move to the original point. Okay, say we have those points, and if we just use a feature transform, it's a linear function, and get the distribution in a new feature space like this with a nonlinear function, then this is the new distribution. And for the new distribution, what will happen? It is possible for us to find a hyperplane to separate the two classes. And if we take a look of its original space, then what will happen? The hyperplane in the new feature space will something like this in the original feature space. So that is the reason why nonlinearity is useful for image classification. It can create some edges in the original feature space. And then there is a web demo. Okay, let's do it. You can try it by yourself. Just click the link and it will launch a website. Okay, and you can do something like this. Okay, say this is the section you can create some network. If I don't want to tangent edge, then let's try ReLU. Okay, then you can change the network. So suppose this is your distribution, and you can see, okay, this is the first layer of your network, And after rerule, let's see, now you only have the first, the positive region. Okay. And here you can also try different, say, distributions. Okay. And finally, you can say, okay. Update your network, and you will see how the distribution will be separated by your linear class, your neural network. Okay, so let's see some examples. Say if we have 3 hidden units. Okay. Okay, then we will get the decision region like this one. And you have 6 hidden units and 20 hidden units. So what does it mean? It means if we have more hidden units, we can find a hyperplane that separates the 2 classes with a very high degree. But sometimes there will be the problem of overfitting, right? Okay. So if we had the regularization term, okay, use the L2 non-regularization term, then we need a parameter to balance the data loss and the regularization penalty. Say for if the hyperparameter is very small, it means it will pay attention on the data loss. So it is still a very zigzagged separation hyperplane. But if we use a relatively large hyperparameter, it means it will pay most attention to the regression penalty. Then you will see the separation plane will be something very smooth. Okay. And the author, he also provided several interesting demos. Okay, let's take a look here. Okay, you can go to this website and yeah, some of them. What we saw is this, and this is the demo for example, this is the Cypher 10. You know the dataset, right? And the author provided an online demo. You can set some parameters, learning rate, momentum parameter, batch size, etc., and run it. And this is the design of your network. Then the website will run the neural network by itself. And for each iteration, so there are many epochs, right? For each epoch, it will show what will be the activation function and what will be the classification results. Okay, so and it will show the loss after each epoch. So from this demo website, you can do something like this. If you are interested, you can copy the structure of the neural network and train it by yourself. Okay. So you see the loss value continually decrease, okay? Because according to our gradient descent, it will find the direction which will maximally reduce the loss function. But sometimes the loss function will increase because stochastic gradient descent will just pick some bunches from our data set. And according to this bunch of images, it may not create the overall decreased loss value. Okay. But however, I say stochastic means statistically it will gradually go to the local minimum. All right, so for students who attend the mini workshop 2 weeks ago, this is the one slide from the mini workshop. And let's see, so what let me explain what the lecturers want to say. Okay, then given the image, you can crop, you use convolutional network to convolute a region, okay, and then generate the second layer. So there is convolution step plus a ReLU activation function. And then you do pooling. Pooling means subsampling. For a high resolution image, you use subsampling. It means for a 2x2 region, you just pick the 4 pixels to 1. Or for a 9x9 pooling function, you pick up 1 pixel from the 9 pixels. Okay, it can reduce the resolution, but try to keep information as much as possible if you are using something like a maximum pooling function. Okay. So with a few steps for convolution and nonlinear function with a pooling is subsampling function, finally you will get images with small resolution. Then you flatten those images. I should not say images because in the neural networks they are no longer images. They are just data. Okay, and you flatten those data. Okay, it will become a very, very long vector, and then you use fully connected layer. It's just a multi-layer perception, the same thing. Okay, it means for every value here, you will use all of them and a nonlinear function to create the next layer. And finally, you do it several times. But again, this one, how many times you should do? That is a hyperparameter, and you need to tune the hyperparameter by yourself. Of course, there are some researchers, they try to develop the algorithms to automatically figure out the best hyperparameters. Okay. Then finally, you will get a few scores. I mean, a score per class. Okay, so this will be our source for our loss function. And when we train the network to reduce the loss value for all of those images for several epochs, then when the test image is given, we compute the scores, and we use the highest score to label our test image. Okay, so Justin Johnson mentioned something similar, something very interesting. This is a property of neural networks. It is called universal approximation. It means if you have a neural network, very simple network, you can use the neural network to approximate any kind of method. Let me recall something. Do you remember a few years ago we said if you have a lot of training samples, you can use nearest neighbor to approximate any function. Okay. Here again, the neural network has the same property. Okay. Let's just use the one-dimensional function as an example. Okay. Say, suppose we have a neural in this architecture. Given the input image, we have 3 weight match value, and of course there will be 3 bias values. And we use the 3 pairs of weight and bias to create 3 hidden nodes. H1, H2, H3 here. Okay, so you can see its equation is here. Then again, from the 3 hidden nodes, we use the same weight, but now I use U here rather than W. And 3, okay, so, and a new bias value, I use P here. So the Y, the definition of Y is this, okay, and the input is X, okay. So what can we do here? Say, if I set a certain N1 and N2 value, then I can create a function like this one. But here, I should say I use 4 hidden values. The first one is this, okay, and the second one is this, and the third one is this, and the fourth one is. Combine the 4 hidden values, I can create the function, and the function names bump function. Okay, so if I have several bump functions like this, so that I can use the bump function to approximate any kind of one single value output function. Okay. But however, if we try to train neural networks, the result is not as simple as just those bump functions. The trained neural net functions may be somehow zigzag, irregular, and etc. But the concept is why neural network is very powerful, because it can be used to approximate very, very complex functions, so that you see natural images are very complex, and neural networks can approximate a very complex function, so that neural networks can be used to classify neural networks and get a very good accuracy. Okay, now you have the concept of neural networks, and you know how to compute loss function, and you also know some gradient descent method. Okay, the problem is if you want to use gradient descent, you need to know the gradient, right? How to calculate the gradient. Suppose you have a very complex neural network, and in the following lectures, there is an existing method called backpropagation. It is designed to compute the gradient of a complex neural network. Okay. So far, because there are a lot of mathematical equations, and I believe it is difficult to understand it then when you just heard of those methods. So I should say, now, do you have any question? All right. I guess it is very difficult to ask questions if you just partially know those concepts. But however, they are mentioned in our textbook. But I should say, our textbook introduced those concepts very, very briefly. And those mathematical definitions, if you want to take a look at our reference book, Goodfellows 2016 New Deep Learning textbook, it provides more information, in particular mathematical expressions for those backpropagation and neural networks and linear classifier, etc. But somehow it is slightly not so easy to understand. The easiest way to understand those concepts, I think it should be Justin Johnson's slides. Okay, so if you cannot figure them out, I suggest you to take a look of Justin Johnson's lectures, because all of them are available in YouTube. Okay. Okay. So now let's go to. So our problem is how to calculate computer gradients for those neural networks. So let's see. Suppose this is our neural networks, and if there are nonlinear score function, okay, and we want to know, and there are also regression terms. Okay, so this is the total loss of neural networks. So what we want to know is what is the partial derivative for those terms. If we can know those terms, we can apply statistical gradient descent method. Let our loss function gradually decrease to the local minimum. Okay? So it means we can create an effective classification function. So, okay, the intuitive idea is, okay, because we know calculus, we just compute those gradients on paper, use the mathematical expression. But however, the problem is the neural network might be very, very large and very, very complex. If you want to derive them on paper, it may be very tedious, very difficult to do it. Oh, so Hinton, they propose, and some other researchers proposed the backpropagation in maybe 30 years ago. Okay, so the idea is they use the computational graph. What is computational graph? It means, say, okay, if I have a variable x and another variable w is a matrix, and I want to express this equation. So what do? I clearly figure out each step of this equation. Say this is, if suppose x equals w times x, then I will annotate there is a variable x, variable w, and there is a multiplication operator. So the result s is somewhere here, okay? And if there are other regression terms, says the w here, and I will plus the regression term somewhere and get the final loss function. When I have the computational graph, then I can compute the gradients step by step, like this. Okay, so this is the example, a very simple example. Suppose I just have three variables, x and y and z, and the equation is x plus y times z. Okay, that's it. So I have x, I have y, and there is addition operator. Suppose I use another variable q here as the result of x plus y, okay? And then there's a z. Then the f value will be the multiplication result of z and the q. So, okay. Then suppose I have their values. X is -2, y 5, and z is -4. Okay. Then I compute. Okay. Q is what? Q is -2 plus 5. So the value is +3. And what is value of f? It is the multiplication of q and z. So 3 times -4, the result is -12. So there is no problem here, right? It is very intuitive. Okay, but what we want is, we want to know the values of the partial derivative. So here, df dx, df dy, df dz is the vector what we want, because this is the gradient of the model at the point -2, 5, and -4. Okay, how to calculate it? So backpropagation, it means let's do it from the end to the help. So the f, of course, it is 1, right? So the value is 1. Okay, then the f dz. Okay, let's take a look. What is z? How do z generate f? It means z times q will get f. So from our calculus course, we know the f dz just equal to q. What is q value here? The q value is 3, we know. So the result it is 3. Okay, and then the f dq. Again, we know the symbol is z, or the value should be z. And we also know the value of z, it is -4. So the f dq is the value of z, so the value is -4 here. Okay, and then we want to know the f dy. The f dy by definition, what it is, according to the Chang rule, it is df dq times dq dy. And the f dq, we know it is -4 here. And here dq dy, what it should be? Because q is x plus y. So the x dy, it should be 1. Okay, so here, this is 1, and this is -4. So the result here, it should be -4. Okay. And so there are some terms here. This is called the upstream gradient. It's from this side. And this is a local gradient. Okay. According to the Chang rule, the downstream gradient will be the result of local gradient times upstream gradient. So here we will, because the q dy is 1, so the value, the f dy is -4. And again, the f dx, according to the Chang rule, again, it is the q dx times the f dy. And the f dq here is 4. And the q dx is what? According to this equation, the q dx is also 1. So this is 1, and this is -4. So the value of the f dx is -4. So, okay, now we have the gradient. The f dx, y, z. We have those 3 values so that we know the gradient. We can do gradient instead. So, conceptually, gradient backprojection just the way from the result, the loss function, go back to its sources. It's the input parameter x, y, z, and for us it will be the parameters w in our neural networks. So when we have for any cases like this, when we have a upstream gradient, and then we can calculate its local gradient and the times then up, then we can get their downstream gradient. So this is just one step. And we have the following downstream gradient, and it will calculate it, use the same method. So this is another example. Say, okay, we have this equation, and because it's w0 times x0 plus, so this is w0 x0, it will, there is a multiplication operator, w1 x1, another multiplication operator, and then sum them up with additional w2, so sum them up with additional w2, and there is a negative operator, exponential operator, and there is an additional operator plus 1, and there is the inverse operator. Okay, So forward pass, suppose we have the values for those parameters is like this one. So this is a forward pass. From those parameters, we can calculate the x value. And okay, now let's see what the backward pass will do. So df this is 1. Okay, no, okay, it is, and then here so the first local gradient is the inverse function, and the derivative of an inverse function is like this one. Okay, so here, because the value is 1.37, let's put it into the x here. You will get this number, and this number is negative 0.3. So this is the downstream gradient here, negative 0.3. Okay, and okay, the local gradient, since this is x plus 1, the x plus 1 dx is 1. So the local gradient is 1. So the downstream gradient will equal to its upstream gradient. It's also negative 5.3. And this is the exponential function. It is still okay. So the exponential gradient is itself. So let's put the value here. Okay. So we generate the result as negative 1.9. So for approximate, for easy to read, we just use negative 0.2 here. Okay. And the local gradient for this function is negative 1. So we use because the value is 1 and the upstream gradient is negative 2, we time them up and get the downstream gradient is negative 0.2. Okay, so here, this is the addition operator. Okay, and we know the upstream gradient. According to Chang rule, so the local gradient with respect to x and with respect to y are both 1. So the downstream gradient keep the same, also negative 0.2. Okay, and this is also another addition operator. So the value doesn't change, also gradient 2. Okay, so here this is the multiplication operator. The local gradient for variable x. Okay, it is y. So here, y is 0.2.0 times the local gradient 0.2. The result is 0.39. Okay. Okay. So why this is 0.39? Because here you see the result is negative 0.19, and 0.20 is just a truncated number. So therefore, if we want to precisely report the number, it will be 0.939 rather than 0.4. Okay, and here again, we use the same gradient. We can calculate the downstream gradient here. So here you see, use backpropagation, we can calculate the W1, the df, the W1, df, the x1, the f, the W2, the x2, the W3. So what's that? That's the gradient vectors for our neural network model at the point 2, 0, negative 1, negative 3, negative 2, and negative 3. So we have the gradient. We can use gradient descent to run statistical gradient descent method to step by step reduce our overall loss. Okay, so here, this is the sigmoid function. Okay, this is the equation of the sigmoid function. It is 1 over 1 plus exponential x. We calculate the sigmoid function in several steps, right? Because we separate each component individually. But however, there is another way. If we just calculate the gradient of the sigmoid function, we use some mathematical equations to derive it. So, because this is definition of a sigmoid function, the derivative respect to x is this like what? It is so the denominator is a square term, and to derive the inner part, it will be like it's still itself. Okay. So that we can rearrange those terms, and then what we get is it is 1 minus the sigmoid function times the sigmoid function. So what can we do for if we have this knowledge? Okay, what we can do is we can combine several steps with the sigmoid function because we know df is 1. Okay, and this is a sigmoid function, and we know the downstream gradient is the value of downstream. So we can use the downstream function by the local value is say 1 minus 0 to 2 times itself times the upstream gradient is here. So we can easily get the downstream function. Okay. Therefore, okay, you see some patterns. If for the forward step, this is add gate. It means if you add the two values to get the new value, then the backward propagation is a copy gate. It means you have the negative upstream gradient as 2, then you will just pass the 2 to its with its local gradient to its downstream. Okay, so if your upstream, your forward step is a multiplication operator, it means you 2 times 3, you will get the result 6. And you have upstream gradient, and okay, what is your output is 2 the local gradient will be the 2 times 5, and you will get the downstream gradient as 10. Okay, so there are some patterns. Suppose you know according to the forward operation, you know what will be the backward operation. Okay. So this is another example. Okay. Say if you have the nonlinear function max, and you have 2 inputs, then for a local upstream gradient max, then you will pass the gradient to the greater value of your input. Because this is a maximum function. Maximum function, you have 2 inputs, and one is bigger and is another small. The smaller one will get no gradient because only the greater one will pass its value forward. And okay, let's see another. Okay, so it means if we have a function and you know how it will be calculated in a forward case, then okay, you can create the corresponding functions for the backward propagation case. And here, okay, this is the grade, because all df function, the value is 1. So it always will be 1. Okay? And if you know this is a sigmoid function, then you know how to calculate it, because this local gradient times is this is a local gradient, and this is upstream gradient, so you get the downstream gradient. And the same for this case, because in the forward case, it is a multiplication addition. So for the backward case, what you need to do is just copy the values. Okay, and because this is a addition, so you just need to copy the value back. And for a multiplication, so you need to do is also a multiplication, but times to the another local gradient. Okay, so you will get the final result. So why do I need to mention it? Because when you use PyTorch or TensorFlow, you use the framework. But how do they do? You know they can calculate gradient, right? But what do they implement the idea? Okay, so there are many versions of PyTorch. For example, now we are using 2.1. Okay, and the first version, okay, the early version was published several years ago. So 0.1.1. Okay, so what's the difference among those versions? Okay, so PyTorch is an open source framework. It means on GitHub, you can, if you are interested, you can go through all of those code. You can see, or even you can modify them by yourself. And there are a lot of programmers, they participate in the PyTorch, and they submit their modified code very frequently. So you can see the version updated very quickly. And say here, there are almost 3,000 contributors. Okay, all of them just write a piece of code. So what I want to say, in the several years ago, most of PyTorch code was implemented in Python, and they gradually migrate their code from Python to C, to C++. So you can see this is the distribution of the PyTorch. Now, less than half of the code is implemented in Python, and roughly the same is implemented in C++, and some of them is implemented in CUDA. So why do they need to be in CUDA? Because GPU can greatly accelerate the computation, even for the backpropagation. Okay. So what I want to mention is, okay, conceptually, because I know the forward path, then I can implement a corresponding backward path. Okay. So okay, now you see the examples of just using a single value. So, but however, our input are images, right? At least it is a vector. So how to calculate the backpropagation for vectors? Then we will discuss it later. Okay, let's take a break now. So, okay, so what about the vectors? You see some examples of scalar values. Vector. Okay, let me say the answer totally the same. But let's go through the examples. Okay, so say what is a vector? It's just a combination of several scalar values. Okay? And say we want the regular derivative of a single value. It is just another value. Okay. If so, the definition from the definition, suppose our x is a vector. So there are n elements. Okay, and our output is a single value y. So its derivative is a matrix. Now, so we know this is the definition. It means if we have a small shift or offset in terms of x, so what will the change in terms of y? And that's the definition of grade. Here, suppose our output is a vector. There are m elements in the output vector, and our input is x, is also a vector. So the derivative is a Jacobian. So it is a matrix of dimension n by n. And for elements in the Jacobian matrix, is a definition of for the jth element of the y vector with respect to the ith element of the x vector. Okay. Therefore, how to calculate the backpropagation vectors? Okay, that's it. So this is the output. It is still a vector. Okay, and our input is a vector rather than a value, because what we saw in our previous class is scalar values. Okay, so suppose we have the x dimension for the vector. Okay, then what we want to calculate is the loss, the z. So it is our final loss is a vector, but here the upstream gradient is a vector because of what? Because of here. Suppose our final loss is a scalar, and input is a vector. Okay, then the gradient is a vector. So here, loss is a scalar, but here the upstream gradient is a vector already. Then we are going to compute the dl, dx, and dl, dy. Okay, it will be two local Jacobian matrix. Later, the size will be dx by dz and dy by dz. According to the Chang rule, okay, the definition of dx, dl, dx, it will be dz, dx times dl, dz. And this is dl, dz, it is a vector. And this is dz, dx, it is a Jacobian matrix. So just do the multiplication, then we can get the dl, dx matrix. So let's see an example. So suppose our output vector is y is 1, 0, 3, 0, and the input vector is also a 4-dimensional vector. Okay, then suppose our dl, dy is 4, 0, negative 1, 5. This is the upstream gradient. Okay, then the Jacobian dx, dy, it is 1, 0, 1, 1. If our f function is a matrix function, it's a matrix. This is a ReLU function. Okay, so say because the input x1 is 1, so its output is 1. The second term is negative 2, so its output is 0, ReLU. Okay, this is a negative value, max 0, and the negative value output is 0. The third is 3, because this is negative, so the output is also negative. Then we compute the dy dx. So for the first term, okay, because it's x, so the gradient is 1. And the second term is 0, so its gradient is 0. So this is 1, 0, 1, 0. So we multiply the Jacobian matrix and its upstream gradient, then we will get the downstream gradient. It's 4, 0, 5, 0. Alright? Okay. And for a root function, its Jacobian must be sparse. Because you see, for this element, it is unrelated to any input elements in the X. So all of them are zeros. Suppose you have a very large Jacobian gradient. Most of the elements are zeros. So this is a sparse. This means only some values on the diagonal are greater than value. Therefore, okay, if you mathematically you should compute the Jacobian and its upstream gradient and get its downstream gradient. But think again, will those contributors of the PyTorch framework do this way? Of course not, because it's very, very slow. You calculate a lot of zeros and you won't use them. Okay, so in their implementation, of course you can imagine, if they know, okay, this is a ReLU function, they won't compute the Jacobian matrix. They just explicitly use their code to check whether input is greater than 0, and then copy those values from the upstream gradient to its downstream gradient. Okay, so this is what they did. They figure out is the input value is greater than 0, then copy the upstream gradient as the downstream gradient. Otherwise, set it as 0. So it can improve the speed of the backpropagation. Also, again, we see our input as a vector. Now, if our inputs are matrix or tensor, so what's the difference between matrix and tensor? So if we have 0 dimension, then it's a scalar value. If we have 1 dimension of vector, 1 dimension of elements, so it is a vector. So if of 2 dimensions of vectors, it is a matrix. So matrix is 2. They are as a horizontal and vertical axis. So how about if we have 3 dimensions, 4 dimensions, 5 dimensions, and 6 dimensions? They all are called tensors. So by definition, the only difference is only the number of dimensions. So, okay, so you can treat them in the same way. So we just use matrix as example. Say X is a matrix of dimensional dx by mx, okay, and Y is dy by ny, okay. The same, the final output is a loss, is a scalar. So, but the dz here, it is a matrix already. Say it is a matrix. Now we are going to calculate the local gradient and use the chain rule by timing the local gradient and the upstream gradient to get its downstream gradient. Here, the local Jacobian matrix, the z dx, it will be a tensor. There are 4 dimensions. dx by dnx by dz by nz. Okay, the same for z. So if you can calculate the local Jacobian matrix, use chain rule, you can get the downstream gradient. Okay, so let's see an example. say Y is the 2 by 4 matrix, and X is the 2 by 3 matrix, and the weight matrix here is 3 by 4. So you can see X times W, okay, it will get the output as Y. Suppose we have the upstream gradient dL dy is here already, okay, and we are going to calculate this dL dx here, and according to the Jacobian matrix, the definition, let me calculate the number of it, okay. For the dy dx, it will be n times d times n times n, okay. And suppose you have a neural network, and the size is m equals 64, d and n equals 4k, okay. Then how large will be the Jacobian tensor? Okay, it will be 64 times 4k times 64 times 4k, and because you use double or float as your variable, so for a float variable you need to use 4 bytes. For a double you need to use 8 bytes. So the total size of the Jacobian here, it will be 256 giga. So it is very, very large. Theoretically, we do it this way, but in practice, there are a solution to simplify it. It means if we want to calculate the local gradient, okay, dy it is a tensor with 4 dimensions. We do not need to calculate the overall tensors just for calculation. We can just take a slice of the tensor. It means dy dx, and we fix the first dimension. Okay. Then what is the value of dy 11 and dx11? Okay. So according to the definition, so y11 here, it is, so here, how do we get the value? The value is from the first row and the first column. So this is the definition of the variable here. And say dy11, dx11, okay? So where is the x11 here? And for the remaining parts, the derivative will be 0. So we can just erase them. So the result will be w11. So for the 4-dimensional tensor, the first variable is what? It's just the first variable in the W matrix. Therefore, we can calculate the second term, y12, dx11. By the definition, the value here, it is calculated by this row and this column. Okay, so definition is here. The result is what? It's just the value. So you can see a pattern, right? Because it is a matrix operator. So if we want to calculate the gradient, most of them are just the value from the W. Okay. So we can see the third and the fourth elements are just the 1 and the -1 from the W matrix. And again, for y21, okay, by the definition and its derivative, its value is 0, because y21 is the summation of the production by the row and this column. Is there x11 here? No. There is no x11 in this equation, so the result must be 0. Okay. And for the other elements, of course, they are all zeros. Okay. Therefore, we can, okay, since we get the dy dx11 here, now we can calculate the dy dl dx because of what? dl dx by definition it is the multiplication of the upstream gradient and the local gradient. And the upstream gradient is here, and the local gradient is here. We calculate it. So this is a dot product. It means element-wise production. So here 3 times 2 plus 2 times 3 plus 1 times negative 3 plus negative 1 times 9. And because all of this is 0, so we can ignore this row. Okay, then we can get the value is 0. Okay. Similarly, we can calculate this term because we do the same thing. Okay, just for different row and column. Okay, so the processing are all the same. Therefore, for a matrix, okay, we can calculate the dl dx for this element and this element. Okay, so you can see for this element, all of the values in the first row are 0 because for the x23 it is on. Is there any term in the y has the x23? Yes, there is, but only this column is missed from the web matrix, the third row. Okay, so I just want to get want to give you a concept. The concept is according to the mathematical definition. Okay, we can skip the step to calculate the very, very large Jacobian tensor because this is a matrix multiplication. Therefore, we can use the properties of a matrix multiplication so that we can calculate the local gradient just by a slice. We don't need to calculate the overall Jacobian, so that we can calculate our downstream gradient. Okay, and this is the way implemented in those convolutional neural network frameworks, PyTorch, TensorFlow, etc. Otherwise, it will require very, very large memory size, and it will become impractical for most computers. Okay, so okay, now we get the LDX. In fact, what is that? It is the upstream gradient times the transpose of the weight matrix. So it makes it easier for us to compute it. Okay? And similarly, if we want to calculate the dl dw, it will become x transpose times dl dy. So see, there is an interesting question. Why this is dl dy times w transpose, and this is x transpose times dl dy? Okay, the reason is because they are matrix. Okay, we say the dimension is n by d, and the dl dy is fixed. This is n by n. So the only way to do the multiplication is put the w transpose after the dl dy. And here, because it is fixed, so we have to use the symbol x transpose in front of the dl dy. So the backpropagation, okay, you can see it is what? So there are many functions, f1, f2, f3, f4, and our input is the x0, the forward passes from x0 through x function 1, we get x1. Through function 2, we get x2. And finally, we will get a scalar loss function. the backpropagation is from this. We want to get its derivative for this variable, and the next, and the next, and go back. So the chain rule told us dl dx0 is what? Is dl dx3, dx3, dx2, x2, x1, x1, x0. Okay. In this case, when we do backpropagation for matrices, so the matrix here is D3 is a vector, and this is D2 by D3 is a Jacobian matrix. So if we want to calculate the dl dx, then we calculate this first, and calculate and multiply it back. So this is why it is called back projection. And because multiplication is associated, so we can calculate, okay, here as first step, so it will still be a vector. And calculate here, I should say this. Okay. In the beginning, we calculate this part, so it becomes a vector. Then from this part, we calculate this part. It is still a vector. And finally, we calculate this part. It is still a vector. So it will be easier for us to calculate. And that's the way they implement in those frameworks. Okay, so for the concept of backprojection, you can find the two books. They all address them in their sections. If you are interested, you can take a look. And let me show you a graph. From our textbook, you can see this is a paragraph written in the backpropagation section. The Richard Selesky cites Goodfellow's book. So this is our reference book. He also cites Justin Johnson's lecture. So you see the three sources. I should say, because Justin Johnson's lecture was given in 2019, and Goodfellow's book was published in 2016, and Richard Selesky's book was published last year. So this is the latest one. So he mentioned if you are interested, you can find resources from somewhere else. Okay, now we are going to introduce a convolutional neural network. Okay. So now we have the neural network, and we also know how to use gradient descent to reduce the final loss. Okay, but what we are going to mention is why neural networks is important. Because it can preserve the information of structures in an image. Okay. So, okay, this is our fully connected network, right? And we have an activation function. Okay. Then, what a convolution layer means? Okay. It means so. Remember convolution function in the second or third lecture. We know. I should put the convolution definition here. Okay. It means for every pixel, if you have a convolution kernel, then you will times the pixels by the convolutional kernel from two directions. It means this is the center point, and you have a convolutional kernel, and this is your input. So convolution means from this point, you will time the pixels in your kernel, and then move it to another pixel from your source, and move your pixel from on the convolutional kernel, and so it will compute all of the multiplication and sum them up. So this is a convolutional kernel. Okay. And they are also pooling layers. It means you have a high resolution image, and you will use the pooling. It means just subsampling. You will create a new data structure with fewer pixels per layer. Okay. And finally, you will have a normalization. So if you, I should say, all of the 1, 2, 3, 4, 5 components are the key points of a convolutional neural network. So let's go through from there. Okay, suppose we have input vector. You can imagine this is an image, and you just stretch it out, reoriginal those pixels just into a very long vector. For the C510 example, the size is 372. Okay, you times a matrix to get the output. Okay, so the output only know what the weighted summation of the all pixels. And now we are going to use convolution kernels. It means given a C510 image, 32 by 32, and there are 3 channels, red, blue, and green. Okay, let's say, suppose we have a convolutional kernel. It is 3 times 5 times 5. Why the first dimension is 3 is what? Is the 3 channel, red, blue, green. And the 5 times 5 is what? The size of the kernel. Okay. Then convolution means you will do multiplication from your input image to your kernel. So pixel by pixel. Okay. Then you will calculate the matrix multiplication plus bias vectors for every possible pixel. Okay, so let's see the result. Okay, for this convolutional neural, just this one single convolutional neural. So what you will get? You will get is 1 by 22 by 22 metric. So why it is 1 by 22 by 22? Okay. So for this region, okay. Suppose I want to calculate the result here at the left top corner. Okay. So I calculate the 3 channel 1, 2, 3 by the 3 channel 1, 2, 3, and 5 by 5. So this is a matrix, a tensor multiplication. Got it? Okay. And then for the next region, I will do the tensor multiplication again. Therefore, when I go through all of the locations from the input image, I will get the layers here. It is no longer an image. It is just a collection of data. Okay. And then I will use an activation function to, usually it's relu. Okay, so generate the output of the first layer. Okay. But however, this is just a single vector. If we have multiple vectors and multiple kernels, it will look like this one. If we have 6 kernels, each of them is of the size 3 by 5 by 5, but we have 6 kernels. So our convolutional kernel layers will be 6 times 3 times 5, so 6 times 3 times 5 times 5. Okay, and our output will be, each of them is 1 times 28 times 28. And the overall, because we have 6 kernels, we will have 6 times 28 by 28. So this is the output image. It is not an image, but this is output. This is a hidden node in our neural network. So can see it is still a neural network, but the structure is okay. So this is our parameters, and this is our first layer of output. In addition to the weight matrix, we also have the bias, because we have 6 weight matrices. So we also have 6 bias values. So we will use it in here. Okay. And then so we will have the output of 20 by 8, 12 by 28, and 6 dimension. So okay, now if we have 2 input images, so what will be? It will be because you know the statistical gradient, it will pick a bunch of input images from our data set, right? So here, if we have 2 images, then there will be 2 times 6 times 28 by 28. It will be our bunch of output. If we have more input images, say if we have n images, and each of them have 3 layers of input. In the beginning, it's easy because we have 3. If you use color channels, color images, there will be 3 channels RGB. But if you use grayscale images, there are just 1 layers of input. But however, no matter for the input image or the midden layers in our network, we can assume the input of the layers, there are n images, and each of them has C-in channels, and the size of those images are h height times width. Okay, so we have the neural parameters or the weight matrix in the middle, and we have the bias vectors. Okay, their dimensions are C out. Okay, then what we will get is a bunch of output, and the overall dimension. You can see, you can view it as a tensor. The dimension of the tensor will be n times C out times h prime and w prime. So what will be h prime and w prime? Okay, let's see. So say if our W1 is 6 by 3 by 5, and okay, and then our second layer is W. There are 10 kernels. The size is 3 by 3. Okay, so the output of the first hidden layer is n times 6 by 23, 28 by 28. Okay. So do you see why this is 28? Because the input width and height are 32 by 32, and the kernel size is 5 by 5. So from the first possible location to the latest possible solution, how many possible pixels can it go through? It will be 32 minus 5, because the width of the kernel is 5, and plus 1, because you can go from the beginning to the end. So 32 minus 5 plus 1 would be 28. Again, here, because the kernel size is 3 by 3, so from 28 minus 3 plus 1, it will become 26. So once we define the size of those kernels and the number of those kernels, we can create convolutional neural networks. Okay. Also, what will happen if we stack 2 convolutional layers? Then we will get another convolution. Now you see there is no nonlinear function here. So we need to add the ReLU after the convolutional care to give it the nonlinearity function. As you know, it is important because the ReLU function or nonlinearity function let us can create a nonlinear separation hyperplane in our feature space. Okay, so our network learn something from our training data, right? And where do they learn? In our weight. So from the input layer to the first layer, they learn something in the weight matrix and the bias term. This is okay. So if we just have one single layer, so that is what we learn from the linear classifier. So it is the templates per class. For the CFA10 dataset, there are 10 classes. Okay. And if we use convolutional network and the nonlinear function, so this is the result of the learned parameters. Okay. They are expressed in the weight. Okay. So if we use a very, very depth network, it means there are many layers. What will it learn? Something like this. Okay. You know AlexNet, right? Just the winner of the 2012 ImageNet challenge. Okay. It has 7 layers, and the first layer learns the patterns. So what you see here is there are a lot of strong edges on this pattern. This is the first layer. So let's recall something. When you have a very depth convolutional neural network, the early layers learn some edges. The middle layer learns some, let's say, textures, and then the final layer learns some structures. So they use the structure to recognize whether the images, there is a dog, a cat, a plane, a boat, or bicycles in the image. So let's take a look of those spatial dimensions. Okay, let's show a very simple example. Suppose our input image is 7 by 7, and our filter size is 3 by 3. So how many pixels can we apply the filter or the kernel? So this is the first one, the left top corner, and this is the second one, and the third, and the fourth, and the fifth. Therefore, we can generate an output image and the size is 5 by 5 pixels. Okay. So in general, we can calculate the output size as if our input width is W, and the width of the filter is K, then the output is W minus K plus 1. Okay. So you can see if we just apply this without any padding, then the image size will shrink. Therefore, some networks, the users they want their image size won't shrink too much. For example, when you go to the when you went to the mini course, there is a UNet. Remember, it means your input image and your output image. We hope their resolution are similar. Okay. Therefore, there is a method to preserve the image size. It just means padding. Padding means because I know my output image will be slightly smaller, then I add some extra pixels surrounding the input image. So there are some parameters. How large will be your padding region? And what will be your padded value? For this case, because our kernel size is 3 by 3, so if we pad the extra values just by 1 pixel, then we can preserve our output image size as large as the input image size. Say, okay, this is input is 3 by 3, 1, 2, 3, 4, 5, 6, 7, and our kernel size is 3 by 3, so this will be our first output, and this will be our second output. So this is 1, 2, 3, 4, 5, 6, and this will be our final output. So the width is still 7. It doesn't shrink. Okay, so very common. Many people they set the padding. It means the extra pixels as k minus 1 divided by 2. So that it will reserve the output size. So, okay, why convolutional neural networks work? Because for an input image, and if we use the convolutional neural network, we will combine the information from a region to just a single pixel in the next layer. So there is a term means receptive field. So from this input and this output, if we apply it for multiple layers, what will happen like this? You see 1 pixel in the output layer. It comes from 3 by 3 pixels in its previous layer, and it comes from 5 by 5 pixels in its previous layer, and it comes from 7 by 7 pixels in the further previous layer. So you see a pixel in the output. It comes from a very large region. It can be what? So say if you have a dog in your input image, it is quite large. But in your output image, it's just a pixel. And if the value of the pixel is very large, you can assume, oh, there is a dog in the input image. So it is the reason why neural networks can recognize structures from the input images. All right. Okay. So, however, there's another problem. Sometimes we want our output images are smaller. See, the padding is we want to preserve the resolution of the input image, but sometimes we don't. We need to further reduce the input image. So there's another term called stride. If we set the stride as 2, then it means from this region we skip 1 pixel and jump to the next pixel. So this is stride. So for this example, we will have the output image of 3 by 3, and you will see those numbers when you try to train a neural network. You will see those terms, and now you can know its meanings. Right? So this is our class today, and we will do our homework 3 next week, right? So just share your findings. Okay, thank you.